Okay, in this video we will be evaluating determinants and using them to Cramer's rule to solve systems of equations. When you have a determinant, typically they're not written with little bracket notation. Typically they're written just with these bars instead, but sometimes it's said that we find the determinant of a matrix. We multiply each diagonal. This diagonal, the first one, is 8/9 times 18. The 9 will cancel with the 18, giving me 2 times that 8. I'm going to have 16 on that diagonal. 5 halves times 4 is 20 over 2, which is 10. And I change the sign of that diagonal to a -10, and then add these two together to get 6. Now the reason I change the sign of that diagonal is really based on the definition. If I had the determinant of A, B, C, and D like this, this is technically defined as A times D for one diagonal minus B times C for the other diagonal. Now I choose, instead of going minus BC, to just add the opposite, and anytime I'm multiplying upwards I change the sign of the product, as you will be seeing in a little bit. Now when we move on to a 3×3 determinant, we have to do things a little bit differently, and I'm going to show you two ways to do this. The first way is to choose a row or column, and you want to choose the one that has the nicest numbers in it, and for us this will be the first row because the numbers are smaller. And then we look at the signs of what we call the cofactor here. Starting with a positive in the top left corner, we alternate back and forth between positives and negatives, just as you have right here. And we watch where the negatives are going to be. This negative is going to line up with this negative, or with that 1 right there, and that tells us when we go through to do an expansion, change the sign of this 1, but leave the sign on the other two, because negative times positive just stays a negative. We're going to do an expansion where we're going to take each number in this first row and multiply it by its minor. Here we go. We start with -3 in the top left corner. The minor is what is left after we get rid of the row and column that contain that number. So when we look at the minor of -3, it's going to contain these numbers down here in the bottom right corner. It'll be the matrix containing 5, 8, 7, and -4. We then move to the next position. It would be a +1, but we're changing it to a -1, times its minor, which is what you get when you skip the middle column in the top row, which will have 10, 6, 8, and -4 in it. And then we have -2 on the top right, times its minor, which is the numbers in the bottom left portion here, which are the 10, 6, 5, and 7. Okay, now we evaluate this expression. We have -3 times first diagonal, -20, minus the other diagonal of 56, minus next matrix, 10 times -4, -40, minus diagonal going up here, 48, minus 2 times 70 minus 30. Okay, let's keep going here. -3 times -76, minus a -88, minus 2 times 40. We've got 228 plus 88 minus 80, and therefore the value here is going to equal 236. Now it asked us, is this invertible? Meaning, would the matrix here that this determinant comes from have an inverse? And the answer is yes. Only when the value of the determinant is 0 is it not invertible. Now that was called expansion by minors. This next process, which I've got shown here, involves a bunch of multiplication rather than expansion by minors. Now I don't have these arrows going downward to the left. You'll see that I do it a little bit differently. And we will use this method for all of our 3x3s. When evaluating this 3x3 determinant, the first thing we want to do is rewrite these first two columns off to the right, as I'm doing now. After that, we're going to begin multiplying diagonals. The first diagonal is -3 times 5 times -4, which has a product of 60, which I'm going to write down below. The second diagonal, 1 times 8 times 6, is 48. And the third diagonal, -2 times 10 times 7, has a product of -140. Adding across the bottom here, we get -32. Now let's begin by multiplying the other three diagonals, but instead of writing the three products down here on the left as shown above, I'm going to put the products up above. So 6 times 5 times -2 would be -60, but I'm going to change it to a positive 60 up above here so that I can add over here at the right instead, adding the opposite. 7 times 8 times -3 would be -168, but we're going to change that to positive 168. And -4 times 10 times 1 is -40, but we're going to change that to positive 40. Adding across up there on the top, we get 268. Putting the values or the totals together for the bottom and the top give us 236, which is the value for this 3x3 determinant. So you really have two choices. You can use this shortcut method, or you can use the expansion method as we showed you a little bit ago.